So in this tutorial, I'm going to look at amino acids. So what we're looking at here are amino acids. There's 20 naturally occurring ones. We get most of them from our food, meat included. So if you're a vegan or a vegetarian, you have to take amino acid supplements. Alright, so we have proteins. Proteins pretty much make up everything in the body, and they are just simply amino acids joined together. So lots of amino acids joined together makes proteins. What we're interested though is the amino acids. So we need to separate those amino acids, break apart the protein, and to do that we use our 6 molar hydrochloric acid. Alright, so in a beaker we mix the protein, we mix the acid, heat it up. That breaks the proteins into the different amino acids. And then we can analyze those amino acids using electrophoresis. Here's the table from page 414. A very important table that you probably use a lot, especially because it lists the isoelectric points. So at the isoelectric point, that is where we have the zwitterion. Okay, so we've got the structure of all these different amino acids here, and take note of the size. So they all have the same skeleton. Okay, so they all have that there. But what we're interested in is the size of the R group, and that ranges from 1 hydrogen in glycine up to things like benzene ring here. We've got a carboxylic acid group, long chain there, an alcohol group, looks like sulfur there, and another alcohol group there. Okay, so some of these molecules can be quite big, and that means they move slowly through chromatography. So zwitterions, this is based on the isoelectric point. Okay, so on page 414, let's take glycine for instance, has an isoelectric point of 6. So that means at a pH of 6, it's going to be the zwitterion. And if I draw that molecule, it's going to look something like this. Okay, so notice with the zwitterion, we have the negative there, the positive there. Basically, we've moved a hydrogen over to here. That makes this negative, that makes that positive. Okay. Now, if I lower the pH, so if I go to pH 5, alright, the pH is lower now. So what that means is the overall charge on the molecule, on the amino acid, is going to be positive. So up here, the charge actually balances out. So that actually balances out. So we've got a net charge equals 0. Whereas here, we're gaining a hydrogen over here from the acid, from it being in a lower pH. So now we have a net charge of +1. So that would mean that this will move to the negative terminal. So if we do an electrophoresis, because it's positive, it will move to the negative terminal. Now at, let's say, a pH of 7, we'll now have the negative form. Okay, so we're losing hydrogen here. Alright, so what we have is a negative charge there. So a net charge now is -1. And if we do a electrophoresis, this will move to the positive terminal. Alright, so what you need to think about is the isoelectric point. Okay, is the pH higher? If so, then it's going to be negative. Okay. Is the pH lower? If so, it's positive. So if you can remember that, if the pH is higher than the isoelectric point, the molecule is going to be negative. If the pH is lower than the isoelectric point, then the molecule is going to be positive. So what we'll end up with is some type of experiment where we're separating the amino acids, and these are gel electrophoresis. So what we've done here is we've put them in different buffer solutions, so at different pHs. So we've got pH 7, 5, and 3. Now what I automatically look for is something that hasn't moved. So this has stayed in the one spot. So that to me says this is the isoelectric point because it hasn't moved. Okay, so what I'll try and do is find some amino acid that has an isoelectric point of 5. Now I got this from the textbook, so let me just quickly have a look, because there's none on page 414 that have an isoelectric point of 5. My apologies, there is one. Cysteine. Okay, so I think this one here could be cysteine. Now I want to prove that. Okay, so cysteine, its Witter ion is this here, and we have CH2SH. Okay, so at pH of 5, this is what it is. Now at a lower pH, so at a pH of 3, lower, it should be positive. Okay, so what I should have is something like this. Now, if it's positive, that means it's going to move to the negative terminal. So at pH 3, does it move to the negative terminal? Yes, it does. Alright, so let's go to a higher pH, pH 7. So at a pH 7, we should have a negative ion. So we should have a structure that looks something like this. And because it's negative, it will move to the positive. Is that what's occurring? Yes, it is. Okay, so that pretty much confirms that that's cysteine. All right. Okay, now let's have a look at example B, because this is going to be slightly different, because I don't have anything in the middle here. There's nothing in the middle here, here, or here. So I don't know what the isoelectric point is. Okay, so this makes it a little bit trickier. What I do know is at pH 11, it has a negative structure. pH of 6, it has a positive structure because it moved towards a negative. And same with pH of 3. Okay, so what that tells me is the isoelectric point must be greater than 6. So greater than 6. I did that run the wrong way, didn't I? Okay, so the isoelectric point must be greater than 6, but less than 11. So if I go to my table, there is only one lysine. Okay, so it's not so tricky after all. So what I would do, my additional test, just to confirm lysine, what I would do is I would run another gel, and I would run this at a pH of 9.7. And what I would expect to find, we use purple, I would expect to find the amino acid sitting right in the middle, because this is the isoelectric point of lysine. So it shouldn't move from there because it's in the Zwitter ion form.